Okay, so good afternoon. We have been discussing about the velocity measurement techniques from last 1 to 2 lectures. Today we will continue the discussion on the same, and today we will specifically discuss about one technique which is known as particle image velocimetry. So let me over here highlight the differences in between the techniques which we studied earlier and PIV. So basically, if you recall, yesterday we discussed about the cross correlation method and other one was hot wire anemometry. Okay, and in both the methods, you have seen that in cross correlation method we had placed two optical probes, something like this. Okay, and in case of hot wire anemometry, we are having some hot wire whose diameter is close to 5 micrometer and length is 1 millimeter, and this hot wire is also placed at certain location in the flow field, and corresponding to the voltage signal obtained from this hot wire we are able to determine the velocity. Okay, you will be coming to know that if you have to use these two techniques, you have to place the measurement probe at certain specific location. Okay, because of which you will only be able to calculate the local velocity, or even more precisely, if you are using, say, set up something like hot wire anemometry, particularly in the constant temperature mode, then you can even obtain the local instantaneous velocity. Is this point clear? Why local instantaneous in hot wire anemometry? Is this point clear? So particularly whenever we are operating in the constant temperature mode, then we vary the current signal, and the dynamic response of variation of current signal is significantly high in comparison to the flow response time, and because of which all the fluctuations which are taking place in the velocity field at that particular location, we can actually measure these. Okay, so this is the difference that in these two techniques what we discussed yesterday, we will be only be able to measure the variation of local velocity. Okay, in certain scenarios this measurement may be important, however in majority of the situations, because measurement of velocity at a single point may not be sufficient enough to completely define the flow behavior. Okay, so our interest may be to know the velocity field simultaneously at each and every point in the flow field. Okay, or of course, because whenever we are using the techniques, experimental techniques, we will not be able to measure continuous variation of velocity field, but at least we should be able to measure the velocity at finite number of points. Okay, so our interest may be to know the velocity at finite number of points within the flow field. For example, even in case of single phase flow, if you have to determine the velocity profile at least along the diameter of the pipe, you should know the value of velocity at least 10 to 12 points, with the help of which only you will be able to construct the proper profile of the velocity. And whenever you will be considering that in this pipe along with the surrounding continuous phase, some dispersed phase is also flowing, and you have to determine that what type of fluidic interactions are taking place inside this bubble, then inside the dispersed phase itself you may have requirement of something around 10 to 15 points along its measured dimension to determine the proper variation of the velocity field within this bubble. Okay, so it means that whatever the techniques we have discussed, cross correlation technique and the hot wire anemometry, with the help of these we cannot measure simultaneously the velocity field at large number of points. If we have to measure at large number of points, we have to place the probes at these many large number of points, and once we will be placing that much big structure of the probes, it will be creating significant flow obstruction and the flow behavior will be significantly altering. Okay, so that's why we have to go for some alternate techniques with the help of which our flow is also not getting disturbed. At the same point of time, we can also measure velocity field at large number of finite points within the flow field, so that we can simultaneously characterize the flow behavior at different locations. Okay. To do so, we will be discussing about PIV, which is known as particle image velocimetry. Is this point clear? So, what we do in particle image velocimetry, say this is my pipe. In this pipe, when flow is entering at the inlet, from the inlet we will be seeding some neutrally buoyant particles in the flow field. Okay. So, what is the meaning of neutrally buoyant particle? A particle which will be flowing with the flow and it will not show any of its own hydrodynamics, because of which the surrounding flow can change. That particular type of particle is known as neutrally buoyant particle. Okay, so it will directly try to mimic the velocity of the fluid medium. Okay, so if I seed large number of this type of neutrally buoyant particle, I will be finding that in my downstream of the flow, I will be having large number of such particles present in the flow field. Okay. Now, if I do image all these particles, okay, then if I take the consecutive photographs of all these particles, then I will be getting multiple images with large number of particles at finite time intervals, which can be delta t. Okay. Now, if I do some sort of correlation in between the two images, and by correlating these two images, I can say that which particle has moved to which location. I can calculate the displacements of the particle, and I know the time interval between the two frames. By using the displacement per unit time, we can actually estimate the velocity at that particular particle locations. Okay, so this is the crude way of explaining PIV. Now let us try to understand what should be the specific features of this system. So here you can see two schematic representations are shown. So this is a cylindrical pipe section. In this cylindrical pipe section, we are having some light source. Okay, this is some laser source, and with the help of this laser source, then we have some optical arrangement. And what this optical arrangement is doing, it is converting this single ray of light into a thin two-dimensional light sheet. Is this point clear? So, this single ray, with the help of some optical arrangement, for example, initially you may have to use some cylindrical lens which will be diverging the ray, and then you can use a spherical lens which will be again converging the ray in the form of a sheet of light. Okay, so we are not discussing about the details of optical arrangement, but the point is we have some arrangement with the help of which this single ray of light we have converted into a thin two-dimensional sheet of light. Okay, and whatever the particle material is there, these particles are of fluorescent nature. So because of which what will be happening, whenever these particles will be coinciding with the laser sheet, these will be resulting in brighter intensity. Okay, and all the particles which are not coinciding with the laser sheet, these will be having the lesser intensity and these will remain dull. Okay, and then we have one high speed camera which is placed in the direction normal to this plane of sheet. Okay, so in this scenario what will be happening, camera will be capturing the two-dimensional images of all these particles. Is this point clear? Now this first type of arrangement is used if we have to use PIV setup for measurement of velocity field in single phase flow. And this is the second arrangement which uses simultaneously two cameras, and this arrangement is specifically used for multi-phase flow. Why we are using two cameras? Because in case of multi-phase flow, what we have to do, we will be having the presence of the interface, okay, because two different fluids are coexisting. So in that scenario, along with determining the particle locations, we have to also determine the interface boundary between the two phases. Okay, so for that purpose, one camera is used to capture the fluorescent particles, and second camera is having some special filter which will be actually filtering out the intensity of the particle, and it will be only capturing the light rays which are reflected from the interface between the two phases. Okay, so with the help of second camera, we will be able to capture only the interface boundary between the two phases, and first camera will be capturing the locations of all the particles. Okay, so this is the schematic representation how PIV setup is used. Over here it appears very simple, but whenever you will be implementing it in practical scenarios, it all depends upon the precise arrangement of the optical devices in order to guide the laser light in a very proper manner. Because if you have even a deflection of 1 micrometer or similar order, you will be experiencing significant deflections in your seat. And one another important point is, whenever we are using this type of system, our seat, laser seat, whatever we are trying to create, as I am specifically calling this laser seat of two-dimensional nature, it means the thickness of the laser seat should be infinitely small. Okay, because if the thickness of the laser sheet is finite, then ultimately what will be happening, whatever the particles are doing translations or motions in the transverse plane, these particles will also be actually captured, whereas our camera will only be able to give the true picture of a two-dimensional nature. So ultimately, the number of particles which are captured by camera, these will be more than the actual number of particles present in a two-dimensional plane. Is this point clear? So that's why the thickness of this sheet should be very small, and at the same point of time, whatever camera we are using, so camera is having certain depth of field. So depth of field of camera should also be extremely small, so that camera is also capturing only a specific location. So say its depth of field may be of the order of 5 micrometer or so, which is smaller than the length scale of the particles which are present in the flow field. Is this one clear? So it may appear, the arrangement may appear very simple, but whenever we go for its practical implementation, it's actually a difficult one. And another important point you have to note it down, it is not kind of a plug and play device that you have fixed this arrangement, you have done some measurement and directly you are getting the value of velocity. So whenever you operate with this type of high-end systems, you have to do large number of iterations, first to calibrate the system, then to understand whether whatever the velocity field you are obtaining that is correct or not, and after you have got, and along with this I will also show you in the subsequent slides that whenever we do the velocity measurement, along with the real velocity field, it also gives some sort of spurious velocity measurement which are actually unphysical. So we have to also identify that which is our physical velocity and which is unphysical data, and we have to remove the unphysical data. Okay. So typically you can see the setup consists of tracer particle, and what should be the characteristics of these tracer particles. So first is they should exactly follow the motion of the fluid. So it means the particle should be neutrally buoyant. Second is these do not alter the flow or the fluid properties. Okay, so there are two things now. First is these should not alter the flow. When particle alter the flow when their characteristic hydrodynamic response time is more in comparison to the flow fluctuation time. Okay, so particle size should be selected in such a way so that the hydrodynamic response time of the particle is less in comparison to the flow fluctuation time. Okay, in that scenario only these particles will not be altering the flow. Second point is these should not change the fluid properties. Now it is very important to know that if you consider say water, and in water if you seed 10,000 particles, okay, so then 10,000 particles, say you have a pipeline of 10-meter length, so these 10,000 particles will be almost in a dilute arrangement will be dispersing in the pipeline, and there will not be any particle-particle interactions. But if say in the same pipeline you have seeded 1 million particles, what will be happening? Or 10 million particles, what will be happening? Your particle concentration within the pipeline will be increasing, and particle-particle interactions will also become significant. So if your sample is loaded with high concentration, then first point is density of the complete mixture is going to change. Second important point is because particle-particle interactions will also come into picture, and whenever particles will be colliding with the wall, these will try to influence the viscosity of the fluid for which we are doing the measurement. So that's why whenever we are using the particles, we have to also keep into mind that particle concentration should not be excessively high, so that the density of the complete fluid mixture is, or density of the reference fluid is actually changing for which we are doing the measurement, or particle-particle interactions are becoming significantly high so that the viscous effects are changing for the overall picture. Okay, so concentration of particles should also not be so small that in the entire frame I am only having 2-3 particles. Then also I will not be able to make a good estimate of the velocity field, and that type of estimate even can be maintained from the hot wire anemometry or optical probe arrangement, etc. Okay, so we should have optimal concentration which is giving proper resolution. At the same point of time it is not changing the properties of the reference fluid, and particles should not interact with each other, because if there is interaction of particles, then what will be happening? Because these are of very small size, so two particles may fuse together and form a larger particle. Say two are joining with each other, so ultimately these may become a larger size particle. And ultimately what will be happening, whenever you will be comparing the two frames, here you will be having two particle locations. In the new frame you will get only a single particle location, so you will not be able to properly correlate your image at the different time instants. Okay, then two or more short laser light pulses with a known time separation illuminate the tracer particle, thus particle appear with spacing proportional to local velocity vector. Okay, so typically what is done, whenever you use this type of measurement, whatever the laser light source we are using, it is not a continuous light source, rather it is a pulsed light source. What is the meaning of pulse? First it will be giving a pulse, corresponding to that this sheet will be generating, then it will be taking some time gap delta t, and after that for the delta t duration this pulse will be stopped, and after that again second pulse of light will be given. Okay, so it means that when you are capturing the photograph, corresponding to that the laser light source is opened in this manner. So there is some duration of pulse, and in between this is the gap during which this pulse is off. Why this is done? Typically in this type of situation, if you give a continuous light, then you will be finding that while camera is trying to capture the particle, camera will try to trace the entire path of the particle. And in your photograph, instead of appearing the single particle locations of bright intensity, you will be finding photograph will be having some dull random streaks. Okay, so that's why whenever the camera is capturing the photograph corresponding to that instant only, we just eliminate the fluorescent particles. Is this one clear? Next is use of electronic cameras for direct recording of particle images. So that also nowadays with advanced imaging techniques it is being used. Now comes the other aspect. Once you have captured the images, what you will be doing with captured images? How from captured images you can determine the velocity field? To understand that, we can have different methods: autocorrelation, cross correlation, and particle tracking velocimetry. Okay, so let me briefly explain this. Say you have captured one frame, and in this frame this is some random arrangement of particles. Now this frame was at some time t1, then you captured another frame at some time t1 plus delta. Okay, now here also you will be having some random distribution of particles. Typically in this type of system, it will be extremely challenging to trace the location of individual particle in the two consecutive frames. Is this one clear? So what is basically done, this frame with the help of some grid, it is divided into large number of subframes. Is this one clear? So each frame is divided into number of subframes. Now this grid is selected in such a way so that each subframe should have at least 10 to 15 particles. Is this one clear? So each subgrid we will be choosing in such a way so that each of these spaces should have 10 to 15 particles in each. Now what we will be doing, whatever this first frame is there, we will try to correlate it with the other subgrids in the consecutive image. Okay, for example, first you will be calculating cross correlation function of, say this is 1 and this is 1 in the second frame. So 1 1 1 2. So you will be calculating cross correlation between these two. Then you will be calculating cross correlation from this to next, this to next. Likewise, for each subgrid in the previous time instant, I will be doing the cross correlation with subgrids in the next frame. And the frame for which my cross correlation function will be showing the highest peak, I will be considering that the particles in that previous system are actually corresponding to that particular frame. Okay, so say this is the frame. This frame has matched with this subgrid in the next time instant. Okay, then what will be happening? this was my origin, this was the origin which is fixed for both the images. If I mark with reference to this point, then with reference to this point, this subgrid has this much delta y displacement and this much delta x displacement. Okay. Now, delta x by delta t and delta y by delta t will be giving me the corresponding u and v components of the velocity. Now, there are two types of approaches which we use over here. One is vortex centered approach and other is cell centered approach. If we are using cell centered approach, then whatever the value of velocity field we have obtained, that value of velocity field I will be assigning for the central point of this particular subfield. If I am using the vortex centered approach, then whatever value of velocity I am getting from this analysis, that value of velocity I will be assigning for all the 4 vortex points of this particular subgrid. Is this one clear?
Here we are assuming that particle will be moving to the next subplane. But what if the particle is moving out of the frame, like it's moving in z direction?
Particles, yes. So that is the reason whenever you capture these photographs in a high speed PIV, there are two type of PIV measurement. One is called as steady PIV measurement and one is called as time resolved PIV. Okay. So whenever we are doing the steady PIV measurement, in that scenario, the nature of flow remains always steady. So it means if any particle, our frame is arranged in such a way, if any particle is going out of the frame, corresponding to that, some particle would enter in the frame from the back side in order to have a balance. Because in steady scenario, there will not be much random fluctuation, and majorly the selection of the plane is such a way so that in transverse direction there should not be any particle movement. Okay, so particularly for steady PIV this will be true, because in case of steady flow, if we have assumed the frame in such a way so that the transverse direction flow is not taking place, then ultimately particle will move only in the parallel plane. But if I go for turbulent flow situation, in case of highly turbulent flow situations, what will be happening? Because the flow situation will not be steady and smooth, whatever care you take in deciding the plane, ultimately always there will be some component of velocity perpendicular to the plane which will be leading to motion of particle in the transverse direction. Now, if say your thickness of laser sheet is 5 micrometer, okay, you will be choosing your delta t time step in such a way so that in between the two consecutive frames, this much distance of particles should not be covered by the particle because of the velocity field. Is this one clear? So ultimately, the selection of delta t is also a important aspect. So, of course, because sheet, though we are saying it's a 2D sheet, but still it is having some finite amount of thickness. And at the same point of time, whatever high speed camera we use, its depth of field is also there. So, it means whatever good quality camera you take, that can go mainly up to say 1 micrometer or 2 micrometer depth of field. So if you are considering that you have 2 micrometer depth of field, you have to select your delta t in such a way so that that 2 micrometer depth of field is actually not changed during the time of your capturing the frame. So this type of PIV where our pulses between the laser light and the camera frame are taken at very small time scales, and these time scales are smaller than the Kolmogorov time scale. Corresponding to that, we will be able to capture the full details of the flow field, and that is called as time resolved PIV. Okay. So all are clear with this idea? Now, what the overall idea is that we have to divide frame into large number of points and ultimately then we will be correlating each subgrid with all the subgrids in the next level, and wherever we will be getting the highest correlation, we will be assuming that frame has gone to that particular next location. Okay. Now it is interesting to note that the resolution of the flow field will be depending upon the resolution of the grid size. What is the meaning of resolution of flow field? Say I have to measure velocity field in this. So from this location to this location, whether I will be getting 10 velocity points or 15 velocity points, these will be governed by the type of the grid I am having. If I am having very fine grid, then I can have more number of points. If I have coarse grid, then I will be having less number of points. Okay, so ultimately the selection of time period at which we are capturing the images and the selection of the grid size, these are another two important aspect which we have to simultaneously optimize to have better results. Okay, so we will be varying these during our measurement, and the instances where the variation in the velocity field will vanish upon further decreasing delta t and delta x, that point we will be considering as the ideal selection. And at the same point of time, always we have to keep in mind whenever we are portioning or smoothing our this one making fine our subframes, we have to keep in mind that each time subframe should contain at least 10 to 15 particles. We cannot go below that, because if we go below that, then we will not be able to make a good estimate of the correlation between the two subframes. Is this point clear? Next point is, so this type of technique is called as autocorrelation or cross correlation technique. Now next is PTV, particle tracking velocimetry. So nowadays we have the advancement in the technology, and there are more advanced laser light source as well as the cameras available, with the help of which we can even try to capture the location of the individual particles. Like I will not try to make correlation for entire grid, but what I will do, I will consider, say this was my old location of particle. For this old location of particle, I will try to create the cross correlation function with all the new particles present in the next frame, and wherever this cross correlation will be working fine, I will be considering that is my new location of the particle. And how this is possible? Because whenever we have advancements in the technology of the camera, so whatever the particle we will be capturing with advanced cameras, these will be giving significant variation in intensity field depending upon the position. So here it will be easy to characterize the behavior of the individual particle. Okay, so here we are trying to capture the each and every individual particle. That type of PIV measurement is called as particle tracking velocimetry, but its use is still limited, and very high and advanced systems and with the help of advanced cameras only we are able to do this, that too for very small visualization windows like in microfluidic devices, etc. For large scale, this type of measurement is still a challenge. But one advantage of this is, in comparison to the subframe based correlation, the individual particle based correlation will give you better spatial resolution. Okay. So this is about the different post-processing methods. In autocorrelation technique, post-processing is performed on a single double exposed image of the flow. So what is done? First an image of previous time, and then on the same frame the new locations of particles are taken, and on that individual frame analysis is done in cross correlation. And of course, whenever we are dividing the image into smaller sub-regions, each contain at least 9 to 10 seeded particles. So this is the formula for auto correlation and cross correlation. And of course, whenever we are calculating this correlation, what we are varying, each and every time we are varying delta x and delta y, and the value of delta x and delta y corresponding to which we will be getting the highest value of this correlation, that we call as delta x star and delta y star. Okay, and that will be considered our actual displacements of the subframe. So I have already explained, we have to iterate this procedure for all the sub-regions, then only we will be able to retrieve the entire velocity field. So you can consider that how much amount of computational resources will be required for creating, for correlating all the subframes. And of course, if you have the time resolved PIV, then you have to do this at large number of time intervals. The same process at large number of time intervals. So in the advanced system, two images are captured on separate frame and then cross correlation between the two subregions is performed, the way I have explained you in the previous discussion. And of course, the disadvantage with these is these have limited spatial resolution, which is limited by the size of the grid. But if we go for particle tracking velocimetry, here determination of displacement of individual tracers is there and it gives the highest resolution. And recently, new algorithms based on some pattern recognition are becoming popular, which are involving neural networks, genetic algorithms, fuzzy logics, etc. And with the help of these advanced algorithms, particle tracking velocimetry is actually becoming popular and gaining popularity. And PIV techniques can be easily used for multi-phase investigations if different phases can be distinguished. So ultimate aim is we should be able to have clear property which can differentiate between the two phases. Then we can simply employ this for multi-phase measurements as well. And of course, when we are using for double camera for multi-phase system, then double camera image acquisition system is required. This I have already explained to you that we have to use filter. And this you can see what are the challenges of using PIV in multi-phase systems. So basically, whenever you are using PIV in multi-phase system, you have to give extra care, because whenever you will be using camera, then you may have occurrence of multiple ghost particles on your frame. Why? Because of the reflection and the refraction effects. So you can see that if you say send a ray something like this, if ray is getting reflected, then at this point, instead of capturing the real particle, it may also capture some virtual particle, and there can be likewise refraction of the rays from the interface. So because of this reason, typically near the interface in multi-phase systems, because of large number of reflection and refractions, whenever we get the final image, in the final image along with the actual particle, we do have presence of some arbitrary virtual particles. And ultimately, this presence of the virtual particles, which are caused because of reflection and refraction at the interface, these leads to formation of large number of spurious currents near interfaces. Okay, so spurious currents, what are the spurious currents? Are the unreal or unphysical velocity values, and unreal or unphysical velocity values typically comes near interface in multi-phase systems because of the reflection and refraction of the particle. So whenever a ray is going, it will be directly captured, that's a real location of particle, but along with that, from the interface there can be multiple other refracted and reflected rays, which will be creating some random virtual particle which are not present actually physically in the system. Now, what should be the characteristics of the light source? So, first requirement of light source is that it should be having short duration of illumination. Okay, so it should be able to give you the pulsed light, because if it is not giving the pulsed light, it is giving the continuous light, then ultimately I told you, instead of getting the point particle locations in our final frame, we will be getting actually streaks of the particle movement. So practical criteria for choice of maximum duration is particle images do not appear as streaks, but it should appear as a circular dot. Okay, so it should not appear something like this. It should appear simply a dot. So if we change this illumination pulse, and unless or until it is matched with the camera capturing frequency, then we will be actually finding that streaks will be coming in the real images. And typically this is possible when particle displacement within the pulse duration is significantly smaller than size of particle itself. So here there is one limiting condition, that pulse delta t should be less than equal to d. D is diameter of particle divided by its velocity, field, and m is the magnification factor if we are using camera with some magnified conditions. Another important point is intensity of light source must allow scattered light from shading particles to be detected by the digital image. So we should use the type of light source so that whatever that light is actually coming from, scattered from the particles, that is detected by the camera. Okay, so normally for PIV measurements, green lasers are majorly used. There should also be some estimate that whatever the laser you are using, what should be its energy. So typically required pulse energy E is always proportional to linear dimension of the area of interest. So area of interest means how much area you want to actually capture. So whatever is its length, depending upon that, if you have large length, then energy will be linearly increasing with increasing the length. If your frame of visualization is small, then the requirement of the energy pulse will also be less. And you can see that laser of energy close to 100 megajoules is sufficient to illuminate an area of about 10 centimeter side, typically whenever we are working in airflow. But if we use the same laser energy in water, then area almost twice the frame size will be possible for water. Why? You can clearly see, if some particle is present in air and you impose light on that, and on the other hand, if you have a particle in water and if you impose light on that, which one will be giving brighter intensity? The one present in the water. Okay, so that is the reason, because of its light transmitting capacity, you will be observing that in water you can, with the same laser, you can visualize more portion. And lasers are used as illumination sources since they can produce pulsed, collimated and monochromatic light beam, which can be easily shaped into a thin light sheet. So there is requirement of monochromatic and collimated light, because ultimately all the particles should receive same intensity of the light. Okay, so if all the particles at different locations, there is variation in their intensity at different locations, then our cross correlation and auto correlation function will not be actually accurate. These are some of the commonly used tracer particles for PIV. For example, if you are using air, and in the flow of air, if you have to seed the particle, then you can use DEHS, glycol water solution, vegetable oil, or TiO2 particles. Okay, and diameter you can see is typically kept in the range of 1 to 3 micrometer, and for TiO2 particle it is 0.2 to 0.5. Okay, and these are the corresponding density values. So density value for TiO2 is high, that's why you can see the size has decreased, because upon increasing the density, the particle response time, if we keep the same size, then particle response time will be increasing, but particle response time we have to always keep less than the flow response time. So that's why, because then only particles will not be interfering with the flow. So that is the reason particle size has to be decreased. Okay, and how these numbers you can calculate? So you can recall in the in some of the starting lectures I have given you one formulation of hydrodynamic response time of the particle. So you can calculate hydrodynamic response time of particle, and parallelly you can calculate the flow response time. So if you have a turbulent flow, then typically by knowing the Kolmogorov time scale of that turbulent flow, you can compare these two numbers and you can choose the particular particle behavior and size, so that the hydrodynamic response time of particles should be less in comparison to the Kolmogorov time scale. Okay. Otherwise, what will be happening? If this is larger than Kolmogorov time scale, then ultimately this particle will actually induce more turbulence and it will change the behavior of the flow rate. Okay. If you have water, then you can use latex particles of 5 to 50 micrometer, sphericell particles of 10 to 100 micrometer, and even you can use silver coated hollow glass spheres of 30 to 100 micrometer. So you can now clearly see that when you are having water, water is slightly more viscous in comparison to the air. Okay, so that's why the characteristic time scale of the water will be larger in comparison to characteristic time scale of the flow of air. So because of which with water we can even operate with larger, slightly larger sized particles. Is this point clear? Now you can see one simple comparison of low image density particle. So here you can see this was the previous location of particle in the previous frame. Now in the new frame, this is the location of the particle. So this type of particle tracking velocimetry will be possible when we have low image density. If we have large number of density of particles, now you can see this is the old image, and old image and new image are actually superimposed on the same frame, where hollow circles are showing the old location of the particle and these solid are showing the new location of the particle in the new frame. Now, can you tell whether this particle has gone to this location or this location or this location? It is difficult to determine. So you can have all the possibilities. So what you will be doing, you will be considering a single particle in the old frame and you will try to correlate it with all the locations, and where you will be having highest correlation function, there actually you will be considering that this particle has gone to that particular location. Okay. Now this is the important point I mentioned about the spurious currents. So here you can see in this grid all these black colored vectors are actually our physical velocity vectors, and these yellow colored long velocity vectors are our unphysical or spurious vectors, which have come because of the errors in our measurement. Okay, so here you can see that how to differentiate between the behavior. You can clearly see if you consider this particular vector, in the surrounding of this particular vector, everywhere you have small velocity value. Okay, and these velocities are oriented in certain specific pattern, and whenever you move from one vector location to another vector location, there is not significant change in the orientation of the velocity vector. Of course, their orientations are changing, but the change in orientation is actually smooth. But if you, in this particular region, if you observe this vector is all of a sudden appearing at any random location, and it is having extremely high magnitude which is not present for the other surrounding velocity vectors, and moreover the orientation of this vector is significantly deviating from the orientation of the surrounding velocity vectors. Okay, so this is how from visual inspection you can compare that whatever the surrounding flow behavior is there, it is completely deviating from that, and this behavior is not present for large number of location, but it is coming arbitrary at any random location. Okay, so this is how you can differentiate, but whenever you will be doing this for say 1 million or 10 million number of points, it will be becoming extremely challenging for you to manually look into each and every location, zoom in and then take out that particular data point. Okay, so typically there are many methods. One of the easiest method could be whatever the changes in position for each and every particle we observed during the given time interval delta t, we can plot these on two-dimensional plane. Okay, so typically what will be happening, whenever your particle displacements you will be observing, all the physical displacements should cluster in certain pattern. Okay, because displacement of particles will not be coming randomly. Okay, of course the displacement will be influenced by the surrounding behavior of the particle. So wherever you will be finding that all the points are clustering in a group, it means that large number of particles are following that particular displacement value. On the other hand, the particles which are just giving you very less number of entries and significantly deviated displacements, these particles you can just take out. So once you take out, these all will be actually coming as nothing but your spurious. Is this point clear? So there are other ways also, and it all depends upon the experience also. More and more you actually work with your setup. So typically, as I told you, all these measurements are not that easy, that this is just a plug and pick type of setup. You have switched on the device, run the experiment and got the output. You have to keep trying for multiple runs and then comparing data for different runs. You have to identify whether you have got your correct data or not. Okay, now what is the advantage of this? Advantage of this is, once you have obtained the velocity at large number of discrete points within the system, then you can utilize this velocity data for characterizing other flow parameters, such as, say, if you have to determine vorticity. What is vorticity for this two-dimensional system? Del v by del x minus. Okay, now you can consider, say, this is your point I comma j. You can apply, say, central difference scheme. So this, using the central difference scheme, this will be becoming v at point I plus 1 minus v at point I minus 1 comma j divided by 2 delta x minus of u at point I comma 2 delta y. Okay, so this is the central difference scheme which we have applied, and with the help of this we can calculate vorticity. Now again, if further we use the stream vorticity method, then we can even use this data for determining or characterizing our pressure field as well. Okay, so it means once we have data available for velocity field at finite number of points within the flow field, it can easily be utilized to determine the other flow parameters. Okay, other than this, of course, here You have seen that all the discussions what we have done, we have tried to characterize velocity field only on a 2D plane. But there are some advanced PIV techniques with the help of which we can also characterize the three-dimensional velocity field. These type of techniques are known as stereoscopic PIV techniques. One of the stereoscopic PIV technique involve transverse motion of laser sheet at finite number of points. So in one pulse, it will be two consecutive pulses it will be giving in one plane, the next two pulses it will be giving in some transversely backward location, third it will be giving in more backward location, and these movements will be so high that almost all the particles will appear as still in the subsequent phase. Because ultimately, whenever we are creating all these pulses, there should not be significant changes in the flow field at the different planes. If you are trying to construct a three-dimensional velocity field, it should be a, if situation is turbulent flow, this measurement should be simultaneous. So you can consider that in milliseconds or nanoseconds time frame, these laser sheets will keep on traversing in the transverse direction. Other technique people use, they place two cameras at certain angles and then they try to simultaneously measure the two frames. So once you have these two frames, data of two frames available, then you can use the mathematical transformations in order to create a three-dimensional velocity field. Okay. So maybe we are not going into the detail of all these methods. This is just about the introductory concepts of particle image velocimetry. So with this we will conclude our discussion on velocity measurement, and in the next lecture we will briefly discuss about the measurement of surface tension.